Right, so this joint work with Andrea Vezzosi, my PhD student, and Theo Winterhalter, who was an intern at Chalmers. Right, and I continue the topic of the first two talks, and there are some similarities, but also differences. So I'm talking about Martin-Löf type theory in a wider sense. So the central thing is the typing judgment. So we have here in context gamma, the term has type A, or you could also interpret this with propositions as types, as under hypothesis gamma's term T is a proof of the proposition A. And so we want to write programs and proofs in the same language. So we have to make sure that the empty type, which is the false propositions, is not inhabited. So there should not be a closed term of type bottom. Right. A central ingredient in this language is the conversion rule, which already came up here in the form of a subtyping rule. So if a term has type A and A is a subtype of B, it should also have type B. And note that there is no coercion. So what we are doing here, we're working actually in the calculus. So the programmer works in the same language as the calculus defines the typing rule and so on. The only thing the tool will do for you, it will infer some arguments which are unique, which you omit, so some hidden arguments. So there is a central notion of definitional equality. So two terms at some type are not distinguished if they follow some pattern, right, which we look at. And so if two types are not distinguished, they are subtypes of each other, naturally. Well, that would be the comment of himself, Per Martin-Löf. He didn't talk about subtyping, sorry, already. Okay, so definitional equality should be decidable because that will entail the decidable of type checking, right? So it can't be the full equality you would maybe expect, the full extensional equality. So we can't have, for instance, the commutativity of addition in general. So usually that will not be part of the decidable equality. It might be, but so far we haven't reached that yet. But so the minimal things you want to equate is all the terms that compute to the same value. Yeah, they should be equal. And the more you add to this definitional equality, of course, the more comfortable it will be for the user as long as it stays decidable. So for instance, in ACTA we have the eta laws. For instance, for the unit type top, so the unit type has just one inhabitant. So whenever I have two terms of the unit type, they should be equal. So this rule has some drastic consequences for our meta theory, but also for what we can do and how we can modify our calculus, because that requires that equality is really directed by the type. For any other type, this would not make any sense. Okay, so my particular work is on size types to certify termination. We need termination for consistency. If you don't have a termination checker, you can easily write a recursive program that inhabits the empty type. That's a no-brainer homework, I hope. So, and for instance, we cannot have this general fixed point combinators to recurse over natural numbers. So this fixed point combinator says to get from a natural number to C, you can invoke the recursive function on any natural number. Instead, we stratify our type, in this case the natural numbers, by some well-founded measure. So here we stratify by the tree height. So for the natural number n, it's in type not I only if n is strictly below I. So this is in quotes because that's not the formal definition, but that's what you should think about. And then we can get this refined type for the recursor that says to construct a recursive function from any natural number to C. If we are looking at a natural number of size I plus 1, we can invoke the recursive function only on size I, so termination is guaranteed by the typing already. And what's nice is we can also have the first class size polymorphism. For instance, that would be the type of a tree traversal, which is parameterized by this size preserving function on trees, and that you can call before you make the recursive call. Yeah? You can modify your tree already before you recurse into the subtree. That's a kind of useful tool. Naturally, we get subtyping. So because it's an upper bound, yeah, we get this subtyping chain for the natural numbers. But this already makes stuff problematic. So consider the successor on natural numbers, which has this type in general, taking us from a natural number bounded by I to bounded by I plus 1. So if we type it with this more crude type, then we can actually put various size arguments here to instantiate this quantifier. So I works, I plus 1, I plus 2, and so on. Infinity also works. And that's because of subtyping. We can either cast first this, for instance, to I plus 1, or we can cast the result to infinity, right? OK, so, well, what's problematic about this is that now sizes show up in terms, but they are not unique, right? The authors of the papers of the first talk in this session might have thought about these problems as well. Okay, so basically we want sizes irrelevant in the terms here, but relevant in the types because clearly not I and not infinity are different types, right? They're only related by subtyping. Okay, so well, why should we stare at slides if we can play with Acta instead? So let's look at the Acta code. So you can also get it from Slack. So Acta is an implementation of Martin-Löf type theory ++. And we have, for instance, inductive data types with constructors. You should all know we can define a predecessor function which cuts at 0, and we can define a subtraction function which basically applies the predecessor y times to the first argument, so it's an accumulator-based function. And then we can, so this is bare Acta with no prelude, so we define everything from scratch. We define an empty type for the false proposition. The unit type is the record with no fields for truth, and then we can define equality on natural numbers by just casing on these numbers. If both are 0, that's true. If both are successor, it depends on what's the result of checking x equal y, right? We make a recursive call here. And so here, a termination checker kicks in and says this is kind of a justified recursive call. In other cases, it's false. And now we want to prove a lemma like x minus x is 0. So here we see our first dependent function type. So it takes an x of type nut and returns something of this type, equal monos x 0, right? And so proving is programming, so let's do this by pattern matching on x. First load the file, certainly. So in case of 0, we have to prove truth, which is very easy. And here, we basically can give anything of type truth because of the eta law. So even a meta variable underscore is fine here because it's eta expanded to the unique inhabitant of, oops, no, I can't do that. Of the unit type. And in the successor case, we want to show the goal again, and note that here we have already, Acta has already simplified. So the original goal was monos successor x is 0, but since monos computes to monos xx, this is the goal we get, and then here we just do the recursive call. Right. So now let's play on. Now let's define division, right? So that's some kind of Euclidean division, basically subtracting y as long as possible from x. So in particular, the recursive call will call x minus y and divide this by y again. But if we try to give this to Acta, it says termination checking failed, because the termination checker doesn't see that the application of this function, which can be, Acta thinks, yeah, it's just a function of natural numbers, that's not guaranteed to be smaller than x, right? So how do we convince Acta? And here size types kick in, and let me see if I can convert this quickly to a sized version. So basically we now make a sized version of natural numbers. Let's for one replace nut by just nut I. Right, and then here 0 will construct a natural number of size successor I, and we need size preload. Acta built-in size. And let's rename the the infinity ordinal to infinity. Right, okay. And then here, so a successor takes a natural number of size I to size I plus 1. Right, predecessor, well, so it doesn't make the size bigger, so it preserves the size. So the I is still an upper bound on the result, and here it's actually a precise upper bound. And the same is for monos. So here we have two natural numbers, and the output is bounded by the input, by the first argument, right? Okay, now we have to give a size argument to 0 and successor, and just let Acta infer it for us everywhere. Let's see how far we get with that. Right, and then we have to add the remaining size quantification. So this is also, it takes one more size argument here now. Right, and these take two more size arguments. Okay, maybe should have done search and replace as well. Okay, so the clock is ticking. Okay, we get there. We get there.
Why don't you use implicit arguments?
Right, I want to show you actually where the sizes get in the way. So I can't do implicit. So actually here we can do infinity. So right. Yeah, but this is a very good suggestion. So I would of course do it. Right. Okay. So let's debug this. All right. Some more underscores. Okay. So, and here Acta is actually dumbfolded. Wait. Okay. So here I have to actually say this should be infinity. Okay. So we got through in 4 minutes. Okay. So what's happening here? If I now, okay. So the first thing is now I should be able to get my division function through. But what happens if I try to do the proof again, right? So I split on x, and isn't this beautiful? The names it generates for you. I spent all Sunday afternoon to fix a regression Acta to show you this beautiful names here, right? Okay, so here we are still fine. This is trivially true. But now here we hit the problem, right? So, so monos of so the monos of successor I, and then here successor X, unfortunately computed to this ugly thing where we still have a successor I and I. So we cannot apply the inductive hypothesis, right? If we try to do this, we get a type error. Okay, so what is going wrong here, right? So the problem is we are using the church-style PTS dependent type quantifier for sizes, right? And this has this rule. If we have two terms at this dependent function type for sizes, and we have a size, then we can apply this, right? But what we actually would want is the Curry-style quantifier, right? Because then we could ignore the annoying size arguments in the terms. So we would like to have this rule where just the sizes here are not even showing up, so they can't spoil our proof. So let's fuse church and Curry style, and we get Curry style. Okay, so what's about Curry style? Okay, well, now we have this rule with the irrelevant size quantifier, and since these arguments are actually not even there in Curry style, so in church style they should also not be having to be related to this B. So actually A prime and B are all arbitrary, I mean at least well-typed sizes. And if we have this rule, of course we also need the rule for typing of an application of irrelevant quantifier. So also here the type argument is not related to the instance. Okay, so then what is happening? We need a different rule for type checking, because otherwise the whole type argument would be pointless. So in the checking, actually we make this argument relevant, so it determines the instance. But the kind of theory behind it ignores these arguments. Okay, so that's the basic argument. I had trouble to extend this beyond sizes, and I don't have time to go into this, but it doesn't work for just, in our case, it doesn't work for system F polymorphism, for instance, because we have eta laws and they break. Right, so we have a condition. If we form this irrelevant dependent function type, the codomain here must be kind of in its shape independent of the x. And things that have the same shape are, for instance, this variance of the natural numbers, but not, for instance, unit type, bottom type, and function type. Okay, so here we have some examples. What is shape irrelevant? Of course, these are shape irrelevant in I, because it only appears on a nut. But for instance, here we have not shape irrelevant, because depending on B, this will either be a function type or not. So here will be the official rules for the irrelevant quantifier. So here we need a shape irrelevant dependency on X. Lambda doesn't do anything interesting, and here, of course, we need this kind of modality applied to the context. So you can hear more about this in the FSCD talk, which was advertised, because I'm getting out of time, and also Per Martin Löf is not favorable on my proposal. So please read the paper for all the technicalities, how to make the theory work, how to prove decidability of equality with a model and normalization by evaluation. And as a take-home message, this irrelevant modality, the irrelevant quantifier, allows us to ignore the sizes where they just help the checker, but not the equality, right? So this is the slogan. Ignore in the terms, but don't ignore in the types. Okay, future work. We want to explore this further. In particular, we want, instead of normalization by evaluation, we want algorithmic equality in order to integrate this with the unification in ACTA. And that will also solidify the implementation, which still has a few bugs. You can prove absurdity and stuff like that. Right. Final word by Martin Löw. Thank you.